All right, so we're going to start talking about rational functions, and today we're just going to dive straight into it, okay? Starting with what is a rational function, right? So let's start with the definition. The rational function, it's got a pretty simple definition. It's some function, let's call it r of x, and it's just equal to a p of x over a q of x, where p and q are polynomial functions. Or in other words, all a rational function is, a rational function, all a rational function is just one polynomial divided by another polynomial. That's all that definition means. Rational function, polynomial divided by another polynomial. And they can be in different forms, but that's what they all boil down to. Okay, and so specifically today we're going to talk a little bit about arrow notation and reciprocal functions, which are a special kind of polynomials. So let's remember a little bit some toolkit functions that you should hopefully be familiar with. 1 over x and 1 over x squared. All right, so these are the reciprocal function and the reciprocal squared function, and they should look a little familiar to you. The reciprocal function is it's kind of this shape. Well, not exactly quite like that. It's kind of like this shape. And the reciprocal squared function is actually very similar, but it's positive on both sides. All right, so these are pretty bad drawings, but that's the idea. That's the shape of these reciprocal functions and the reciprocal squared functions. And we could talk about a lot of things of here. We could talk about domain. Where are these defined? What are the x values that we can plug in? Everything except 0. We could talk about the range. They have different ranges. They have different y values. We could talk about asymptotes. And indeed, we are going to talk about asymptotes in the next video. Both of these have asymptotes at x equals 0 and y equals 0. X equals 0 is this line. Y equals 0 is this line. We could talk about end behavior. We did a little bit about that in 5.2 and 5.3, right? For end behavior, we would say, right, that as x goes to infinity, in fact, it doesn't matter whether x is going to positive infinity or negative infinity. So we could say as x goes to either direction, plus or minus infinity, as x goes to the right, or as x goes to the left, what's happening to each of these functions? Each of these functions to the left and to the right are approaching 0. Okay. Now we're also going to talk about something called local behavior. All right, and that's something a little new here. Local behavior is going to, a lot of times, going to talk about vertical asymptotes. Local behavior means a lot more than that, but a lot of times in this section, we're going to be using arrow notation on vertical asymptotes. Okay, so let's look at this vertical asymptote right here. Well, if we approach the vertical asymptote from the left, we're shooting down in negative infinity. If we approach the vertical asymptote from the right, we're shooting up to positive infinity. So this vertical asymptote depends on, are we approaching 0? Are we approaching x equals 0 from the left or from the right? So we need notation for that. So each one of these is going to have different local behavior. Here we're going to say as x approaches 0 from the left, that's a negative in like the superscript. It's not an exponent, it's a superscript, just like in the word second. So as x goes to 0 from the left, the function goes down to negative infinity. As x approaches 0 from the right, I bet you can guess what goes here. From the right, the function approaches positive infinity. So try to mimic this for the other graph. And what you should get is as x approaches 0 from the left, the function approaches positive infinity. And as x approaches 0 from the right, the function is also approaching positive infinity. So in the second one, it doesn't matter whether we're approaching 0 from the left or the right. It's going to positive infinity in both of these. All right. So let's kind of clarify this a little bit and more formally introduce this notation. If x approaches a with a negative sign up there in the superscript, that means x approaches a from the left. And you can remember which one's which by thinking about a number line, right? On a number line, the negatives are on the left, the positives are on the right. It's the same thing here. We're approaching from the negatives from the left. And similarly, x approaches a from the right, means x approaches a from the right. Okay? And again, as a reminder, we can also maybe think ahead towards like calculus or something. And these things can also be written with limit notation. And I'll show how this looks in limit notation when we do our example problem. All right. Example 1. Use arrow notation or limit notation to describe the local behavior. We can abbreviate that LB, and end behavior, which, just like before, we can abbreviate that EB. These are not necessarily normal abbreviations, but save some time. First one, do y equals 1 over x minus 2 plus 4. As a side note, you might say, Jason, this does not have the form of a rational function. You said a rational function was a polynomial divided by another polynomial. Well, if we wanted to, we could get a common denominator. That'd be x minus 2. And you get like 4 times x minus 2 plus 1, I think, over x minus 2. And now it's a polynomial divided by another polynomial, and you could simplify and stuff like that. So yes, this is indeed still polynomial function. Sorry, a rational function. It can be written as a polynomial divided by another polynomial. So we could use function transformations here and what we know about reciprocal functions. All right. Or you could graph it on Desmos, but let's get some practice. All right, let's say we have this. Normally 1 over x, right? Normally 1 over x kind of looks like this. We just covered that in the last page. Well, what are we doing to it? We're moving 1 over x right to, oh, that's going off the board. Y'all can't see that. Right to and up 4. All right, remember your function transformations. Subtracting a 2 on the inside of the function moves it to the right. Adding 4 on the outside of the function moves it up. So this is just our regular reciprocal function moved right 2 and up 4. So if the asymptotes are normally at 0, well, now the asymptotes got moved to the right 2 units. All right, now we have a vertical asymptote right here. It got moved up 4 too, so the horizontal asymptote is no longer at 0. Now it's up here. All right, I didn't give myself enough room for this graph. And then we can make a little sketch, right? just use the same shape as before, and we know this is what our function's looking like, and we can use this to describe the local and end behavior. Definitely should have done this on the next page. Watch this. It is now on the next page. Flawless. Flawless. All right, so let's answer the question. To the end, let's start with the local behavior, right? Local behavior means, for purposes of this section, it wants to know what's happening around that vertical asymptote. Well, as x approaches our vertical asymptote, which is at x equals 2, as we approach from the left, the function, what's happening to the function as we approach this vertical asymptote from the left? Well, that's approaching like this. This function's going downtown, off to negative infinity. And similarly, you could do the same thing approaching from the right. The function goes to positive infinity. That's our local behavior. End behavior going to be as we go to the left, we're approaching a y value of 4. As we go to the right, we're approaching a y value of 4. So as x goes to either positive or negative infinity, this function is approaching positive 4. And that is how we do it. Again, you can just graph this with Desmos if you want. All right, I'm okay with that. But this was good practice for function transformations and toolkits. And actually, instead of doing a part B, I want to make a quick note about limit notation. You can also use limit notation on here. You'd write it as the limit as x goes to 2 from the left of the function is negative infinity. And the limit as x goes to 2 from the right of the function is positive infinity. And the limit as x goes, we don't usually use the plus or minus here, or at least I haven't seen it. Negative infinity of the function is equal to the limit as x goes to positive infinity of the function, which is equal to 4. This is another way of writing this with limit definition that's very commonly used in calculus when we start more formally talking about limits. We're not really formally talking about limits here. We're just kind of introducing them conceptually. Okay. And then here is some notation that you could see in the future. So all you need for this class is the arrow notation. But if you're moving on, the limit notation might be good to get used to. And I think it's a little more succinct, right? It's a little bit more compact. I'm a big fan of compact. All right. So that's local and end behavior. Let me know if you have any questions, and good luck.